stacks and queues such a simple concept is the fact that we won't be carrying out any insertion or deletion operations anywhere in the middle of our data structure. So in a stack, you'll be simply popping off the element from the ending of the list. So as I said previously as well, a stack data structure follows the last in, first out principle. And if you want to reach the first element of your stack, you'll have to first pop off the last element of your stack and keep on iterating that way. And by the end, you'll be able to empty your stack. So let's get started with the operations and initialization of our stack. So you can compare stacks to a can containing tennis balls. As I said, you can push various tennis balls into your stack one by one. And by the end, if you want to access the first tennis ball, you can't directly access it without first popping off your second tennis ball. Now you add a third tennis ball to your can. And if you want to access your second tennis ball, you'll have to first get rid of your third tennis ball. So this is basically the concept of last and first out principle that is used by our stack data structure. Okay, now we shall be initializing our stack data structure. So as I said, we'll be implementing stacks using the concept of linked list. And so for that, we will be considering every element of the stack as a node. So for that, we will again define our node class. Let me show it to you again. We will be having our node class, our init function, which will be taking in the value as its parameter. Then the self dot value will be equal to value, and the self dot next will be equal to none. Now we'll be defining our stack class. So as usual, we will be instantiating a new node object from our node class. And instead of having a head and tail in a stack, we will be calling it top and bottom. But in our case, we wouldn't even be taking in the bottom variable. We'll simply take the self.top variable, and as usual, the length or height of the stack will be also initialized. So whenever you initialize your first stack, you will be essentially creating a node which will have its next pointer pointing to none. Just take a look at this code. Now we shall be running it. As you can see, we have created our stack class object. And after we run it, we can see the value 4 has been printed out. Now we'll be carrying out our push operation on our stack. Now, as we have already studied so many operations on our linked list, and as we are implementing our stacks and queues data structure using linked list as well, if we want to push a new element onto our stack, essentially we will be taking the next pointer of our new node, and we'll simply, again, we will be carrying out manipulation on our next pointers. So we'll simply take the next pointer of our new node, and we'll point it toward the the already existing uh, top variable of our stack class. And then we will simply assign the value of top to the new node. It is similar to what we did in our linked list operations. Simple. Now, again, if our stack is already empty, then for that also we'll have to write our different conditional, which will be, anyways, we will be instantiating our own object of our node class. And if your stack is empty, then you'll simply initialize self.top to be equal to new node. Otherwise, if you have to push a new element onto your stack, you'll, as I said, you'll take the new node dot next pointer and you'll start pointing it to the top node of your stack. And then you will simply declare your, and you will assign your top variable to your new node. Any confusion here? Is it clear? And as usual, you will be increasing the height of your stack. So let's run our custom input on this. Okay. So we had our first element initialized as 2, and we'll be pushing a value 1 onto it. Let's take a look at this code, and after we run it, we see that our first element was 2, and on top of that, you will see that 1 has been pushed on top of your stack. Any doubts until here? I'll take that as a no. Concept is quite easy to understand actually, so I don't think there would be any doubts by now. Now we'll be declaring our pop function for our stack class. So as usual, if your stack is empty, you would not be returning anything. So you will declare return none. And okay, again, I would like to ask you guys to answer what will be happening. Okay, Mlc Krishna. And go to head. Go to this code that you've given. Is it for push, Vamsi Krishna? Okay. You said current node equal to head, which means the first node, and new node equal to the new node. Okay, you'll initialize the class object, and then new node will be equal to current node. Um, so your function will be assigning the value of new node to be equal to the current node, which is actually the first element of your stack. When it comes to a push operation, we will be simply appending the new node value to the last element of the list. We will simply take the pointer of our new node and point it to the last element. So what your code does is it will take its new node and it will be assigning it the value of current node, which was previously assigned to the first node. I don't think it would run. You can try running the code and check for yourself, but I'm not really sure about this. Okay, let's continue with our next function, which is the pop function. Does anybody have any idea on how we will be implementing our pop function for our stack data structure? So in our pop function, essentially, if the stack is empty, we won't be returning anything. And if we want to pop an element from the end of our stack, we will simply take a new variable, which will be the temp variable, and it will be equal to the self.top. And we'll simply assign the value of self.top to be equal to the next element after the temp node. And then we'll simply take the next pointer of our temp and we'll equate it to none. And that way we will be getting rid of our last element and we'll be assigning the self.top value to the next element. And we'll be decreasing the height by 1. So let's take our custom input. We have this stack object implemented here, and we will be essentially removing the last element of our stack using this pop method. So we initialized our stack. First element is 7, then we pushed 23, then 3, and then 11. Now we will be popping off our 11 node from our stack. After we run this, we'll see what happens. You'll be return this node object. So as I said earlier, this is Python's way of representing node, this object's memory addresses. If we want to see if our code has run successfully, you can say return temp.value. But if we want to ensure proper execution of our code, we won't be writing temp here actually. We will be writing we won't be writing temp.value. We will be writing temp, return temp. And here Prabhakar has given the answer. Can you tell me what is this data supposed to mean in your code? Okay, Venkata Dhanush, it's working. The elements. Okay, so are you saying that we will be iterating through our stack? Is that what you're saying when you say data? Are you going to like declare a for loop or an if conditional if you want to get the data, the elements of our stack? Wait for your answer. In the meantime, let's continue on to our next data structure. Now we are done with stacks. Now we'll be moving on to queues. So in our stack data structure, we have our last in first out principle implemented. And in our queue data structure, we have a first in first out data structure principle implemented. So as we study our next concepts, we will be learning about the concept of graph traversal. And in that, we will be implementing a breadth first search algorithm. And in that algorithm, we will actually be implementing our queue data structure to ensure smooth execution of your algorithm. So there are two methods to implement a queue. You can implement it using a regular list or a linked list. Actually, when we use our queue data structure in our breadth first search algorithm, we will be declaring queue in a regular list. But for this session, we will be implementing using a linked list. So let's just take an overview of what a queue exactly is. You have your first element coming in, the next element, and when the exit first element to be added will be the first element to be exiting the queue. So this is the first in first out principle. Now let us initialize our queue constructor, our queue class. So every element of your queue will be a node. So we'll define our node class as usual, and then we will be declaring our class. Then we have our init function, which will be having self.first and self.last and our new node. And we'll be initializing the length to be equal to 1. So in a stack, the first element is the top element. No, it's the bottom element, and the last element is the top element. And in a queue, the first element is called the self.first, and the last element is the self.last. So now we'll be initializing our queue custom input. As you can see the code here, after we run it, we'll simply have 4 pop out in our console. Okay. Now we shall be studying the operations on our queue, which will be enqueue and dequeue. So I would like to again ask you guys to send the code for our enqueue operation. Enqueue is basically just adding a new node to the end of our queue. Wait for your answers. Any answers? Does anybody have an idea how we'll be implementing our enqueue method for our queue data structure? Okay, let's continue. So if your queue is an empty list, we'll simply declare the first and the last variable to be equal to our new node, and our function will, as usual, declare its own instance of the node class. And if the list is empty, if the queue is empty, we'll simply equate this first and last parameter to be equal to our new node. As you can see here, if self.first is none, then we'll be declaring first and last element to be equal to the new node. Else, if you have an already existing queue data structure and you want to enqueue a new element to it, we will simply take the next pointer of our last variable, last element of our linked list, and we'll take the pointer and start pointing it towards our new node. And then we'll simply assign the self.last variable to be equal to our new node. As you can see here, self.last.next is equal to new node, and self.last is equal to new node. And we'll be increasing the length by 1. Now let's run our code with a custom input. We had our first element to be equal to 1. Now we'll be enqueuing 2 into our queue data structure. So after we run our code, you'll see that first 1 will be popped out and then 2 will be popped out, as you can see here. Any doubts until here? I think this is really easy because we have already studied the concept of linked list, so I don't think anybody would have any doubts in this. Now let us take a look at our dequeue operation. Again, if your list is empty, then you'll be returning none, because if your list is empty, then there is no node to return. And now if your queue data structure is not empty, then this is how you shall be implementing your dequeue method. As you can see, yeah. One more thing, if your data queue data structure has the length of 1, then you'll simply take the first and last pointer and first and last variable and start equating it to 1, none. As you can see here, temp equal to self dot first, and if the length of your queue data structure is equal to 1, then you simply equate the value of first and last to be equal to none. Otherwise, we have already equated temp to be equal to self dot first. And now we'll be bringing up our linked list here, our queue data structure, and temp is equal to self dot first. And as in our queue data structure, we have our first and first out principle. We'll simply take the first element's variable and we'll be assigning it to the next variable. And then we'll simply take the next pointer of our temp node and we'll equate it to none. And this way we'll be getting rid of our first element from our queue data structure. And since we're dequeuing, we'll decrease the length by 1 and you'll return the deleted node. Now let's try to carry out this operation on our queue data structure. So you had a queue data structure with 2 and 1. Now We will be carrying out a dequeue operation 3 times on it, and we'll see how it runs. We first print our queue data structure. We find 1 and 2. And now we will be carrying out this dequeue operation on our queue data structure 3 times. So first you will be deleting the first element of your linked list, which will be 2, and then after that you will be returning 1, and after that you will be returning none. If you want to see the value, you have to return temp.value, as we have seen earlier as well. Yeah, no, in this recording, they have written it in a wrong way. After you first run your dequeue function, the first element will be popped out, which is 1. And then after that, 2 will be popped out. And then none shall be returned, because after that, your uh, queue data structure will have become empty. Today's session was really small and I think pretty easy to understand.